equations and the matrices. And this time we will continue work on 5.3 eigenvalues and eigenvectors. And this is really the definition part. Okay, and also keep in mind the eigenvalues and eigenvectors, they are just defined for square matrices. And A is a square matrix. And if we happen to have this situation, A times a non-zero vector equals the scalar multiple of that vector. And if that is the case, lambda, it is the eigenvalue, and also the vector, it is an eigenvector corresponding to lambda. And also usually for a matrix, and there are multiple eigenvalues, and for each eigenvalue there is a set of eigenvectors. Okay, and I think we already solved this one in the previous video. So how about let's work on another example. Also maybe for reviewing purpose, it's easier, well, it's helpful to take a look how we can find out eigenvalues and eigenvectors. First of all, you really want to set up the characteristic equation of the matrix. And then indeed, the characteristic equation, it is a polynomial equation. And then we solve the characteristic equation, and the solution, they turn out to be the eigenvalues. And then for each eigenvalue, you want to find out a corresponding eigenvector. How about this time we move to a totally new example, not that totally new, but anyway, I think this might be helpful. It's, well, without knowing the answer in advance. Okay, so the matrix is 2 by 2. And again, basically what I did here is first I set up the characteristic equation. It is always in this fashion: A minus lambda I, the determinant. Okay, this is 2 by 2 square matrix. Remember, it is included with the pair of vertical bars. That's the determinant. So we calculated the determinant using the normal arrangement: 1 minus lambda times 1 minus lambda minus 4. And then you want to multiply this out. And then indeed, you multiply them out using the Fourier rule, it turns to be a quadratic polynomial. And then we set this A minus lambda I equals 0. That is the characteristic equation, right? So in this case, it is a quadratic polynomial equation, okay? And then we got 2 roots from there. It can be factored. There are 2 eigenvalues, 3 and a -1. And then for each eigenvalue, we look at A minus lambda I times V again, and it is always a homogeneous system. So indeed, for now, I still have V1, V2 listed as components. Later on, actually, in my next example, I just skipped those vectors because we are always having homogeneous systems. We are always having a homogeneous system. That means we really don't worry about the right-hand side. And for the left-hand side, for the coefficient matrix part, we only need to have the coefficient matrix, not about V1, V2, those components. Okay. So in this case, I think it's rather easier to see one related scalar multiple of other. So we are really having one single equation with 2 unknowns, which means that we do have many solutions. I believe I just started from the first equation. So from the first equation, it's simply say the 2v1 has to be v2, right? Using the matrix multiplication. And so you can find out many solutions. How about I'm just setting v2 as, I'm setting v1 as 1, so v2 would be 2. And so 1 and 2, it is eigenvector corresponding to the eigenvalue 3. And indeed, don't forget any scalar multiple, because the system we consider here, it always in the situation has many solutions. So I'm saying any scalar multiple of this vector could be an eigenvector here, okay? Certainly for simplicity, I'm going to say this is an eigenvector here. Then for the other eigenvalue, -1, pretty much I repeated the same thing. I repeated the same thing. I repeated the same thing again. Okay. And indeed, you take a quick look at the coefficient matrix. I hope you got the idea. We really only needed to work with the coefficient matrix. One row, it is a scalar multiple of the other, right? So it really means we are only having one equation for two unknowns, which means we are having many solutions. And also, I hope you remember this system always got to have many solutions because we already made this matrix as singular matrix. It's non-invertible. Okay, so it has many solutions. Indeed, from the first equation, I'm seeing 2v1 is negative v2. So you could choose v1 as 1 and the v2 as -2. And then that would form an eigenvector for this thing. Actually, I suppose I guess I need to use notation v2 here. Okay. And also, again, about notation, all the v's without arrow is totally different from the v's with the arrow. Okay. Without arrow, I meant to say those are scalars or components of the vectors. With an arrow, like here, there, and here, these are the vectors. These are the vectors. So far, so good. How we find out eigenvalues and eigenvectors. So I say this probably should be considered as a step 2. Okay, 2 steps to find out eigenvalues. Identify the characteristic equation and then solve for it. Step 2, you want to solve for the solution. Okay, from the characteristic equation, it is the eigenvalue. And then step 3, you really need to work with each eigenvalue. Then for each eigenvalue, really there is a set of eigenvectors. Usually you only need to identify one or two. I should have mentioned that indeed for each eigenvalue, okay, the corresponding eigenvectors form a vector space. So that is what I meant for each eigenvalue. You only need to find out one eigenvector. And also it is possible in some cases for one eigenvalue, you may need to identify 2 different eigenvectors or even more, okay. But anyway, for the example, we only consider one eigenvalue represented by one eigenvector. How about we work on one example, and it is a 3 by 3 matrix. And this is a 3 by 3 matrix, square matrix, and we want to find out the eigenvalues and eigenvectors. So the first step I did here is just to consider the characteristic equation. A minus lambda I. It is the characteristic equation. It is the determinant based on this matrix. Okay, A minus, not the matrix, only it is in the fashion of A minus lambda I. And then, well, let's take a look at what is A minus lambda I. And this time it might be, I don't know, it might look pretty complicated, right, even for 3 by 3. So, quick reviewing purpose, for the determinant of 3 by 3 square matrix, you can expand the determinant, calculate the determinant from any row or any column. Usually it is better if you choose a row or column with zeros. So this is what I did. Okay, I chose the first column because there is 0 as the last element. And then I use cofactors. So the cofactor of this element from row 1, column 1, we have this -1 to the power row index plus the column index. Then multiply by the number itself, then times the determinant of the minor. The minor of the matrix, it is generated by crossing out the row and the column. So that's a 2 by 2. Hopefully I got it right. I'm calculating the determinant using the first column. So the second cofactor I consider here still starts from -1 to the power. But this is row 2, column 1, so -1 to the power 2 plus 1. And also the element itself, it is -1. So I got another -1. Then the determinant of the minor. Determinant of the minor, or really the minor, it is generated by crossing out the row and the column where the element is. So this is the minor. 1, -2, 1 and a -1 minus lambda. That's the minor. And also I do have the third element I didn't consider, but anyway, because the element itself is 0, so I really don't even need to bother about the -1 to the power and the minor part. It must be 0. Okay. And then this part may take a little more calculation. I would say if you are watching the video, you may want to pause a little bit to take a look if all the writing makes sense to you. And simply by listening may not make a lot of sense. Okay. First, I did consider this -1 to the power. But anyway, this is plus sign, right? -1 to the power, usually it only gives plus or minus sign. So this is a plus sign. And still this is 1 minus lambda here. And also I look at determinant. This is the diagonal line minus the other the back with the diagonal line here. Okay. And then for the second part, this is a negative. But there's another -1. Actually, still tends to be positive. Still tends to be positive. And then for this 2 by 2, this one is rather easier. It should be -1 minus lambda, and then minus -2. That's plus 2. So I believe this should be -1 minus lambda. Yeah, I have plus 2 in the end. Or maybe I think it might be helpful if I add another pair of parentheses, just to indicate that these two are from this part of the determinant. And then, as I'm saying, if you are watching the video, do pause a little bit. Take a look if the writing makes sense to you. I'm saying you really don't want to rush to multiply everything out. Okay, so I kept this 1 minus lambda in the front. I just look at the things inside this pair of parentheses. I expand this product using the FOIL rule, and then also I believe I combine this -1 in the end here. Okay, let me take a look if I'm correct. So if we do the FOIL rule -2, then that would be plus 2 lambda or minus 2 lambda, and then minus lambda plus lambda. That's negative lambda. Then negative, that's lambda squared. Still there's -1 in the end. There are 4 terms. And for these terms in the second pair of parentheses, -1 plus 2, that's 1, right? And indeed, I say it might be better if I just write this as 1 plus, put this +1 in the front. Put it in this fashion, it will be better. Put 1 minus lambda. So you can see what I'm trying to do next. Don't rush to multiply everything out. It makes things more complicated, okay? So through careful manipulation, at this moment, I'm seeing 1 minus lambda is a common factor. You can take this out. And then these things, and take out 1 minus lambda in the second pair of parentheses, there's still +1 left. So this -1 plus 1 would cancel. So there's -2. And then for this part, it can be factored again. Lambda -2 and the lambda +1, right? And the characteristic equation, it is by setting this determinant equal to 0. That's what I did. And then, as I'm saying, that is the step 2. There are 3 eigenvalues. 3 eigenvalues. lambda 1 equals 2, lambda 2 equals 1, and the lambda 3 equals -1. And basically, this is the example from the textbook. So I'm trying to identify lambda 1, lambda 2, lambda 3, and in the same order as on the textbook. Okay. And then the last step, step 3, it is to find out the eigenvalues. This time we are going to consider those 3 by 3 systems, right? 3 by 3 square matrices. Okay. So for lambda equals 2, we consider the system like this. Keep in mind that we want to solve for v, right? And also, according to our arrangement, there are many v's. Such a system always have many solutions. And besides the right-hand side, it is always 0. So we are really working with a homogeneous system. So the next line here, I really only consider the coefficient matrix A minus lambda I. Okay, A minus lambda I. And if you forgot A, or actually you can consider from here, replace lambda with, I'm doing the first value 2. So I'm getting the matrix in this fashion. And basically, to solve a system, we are using elementary row operations, and we want to get the row reduced echelon form. So this is what I did. This means from this matrix, first row 1 multiplied by -1, then update this row 1. So really this will be 1, -1, and 2. Okay. And I'm thinking this one as a pivot, And then use new row 1, add to row 2. Because in the column where the pivot is, the other elements have to be 0. So I'm adding this updated row 1 to row 2. So 1 added to -1, that's 0. And this -1 added to 0, that's -1. And then what I have, 2 added to 1, that's a 3. And then I hope it's quicker to realize row 2 and row 3, they are equivalent, right? So row 2 and row 3, they are equivalent. And furthermore, I did change, well, to reduce some operations, I just interchanged the row 2 and row 3, So this one, it is a pivot. And row 3 really can be eliminated as a 0 row. And the last thing what I did here is, I think there's another thing I did. I add this row 2, just because this is moved to add row 2. Row 2, it is add back to this row 1. So this is really the so-called row reduced echelon form. And well, basically this equation simplifies V1 minus V3 equals 0. So V1 and V3 got to be the same. I'm considering V3 as free, so I'm taking V3 as any real number as t. And the V1 should be that same number. And then from the second equation, we can solve for V2. V2, it is 3 times V3, or 3 times t. And indeed, I hope you recognize the solution really it is a scalar multiple of 1, 3, 1. 1, 3, 1. The scalar. And any scalar multiple, it is a solution. And any solution, it is an eigenvector, right? This is where the eigenvector is defined. So I said, well, I'm just taking out 1 as the eigenvector. Okay, 1, 3, 1 as an eigenvector, which is corresponding to lambda 1 equals 2. And also do note, any scalar multiple, if you take a 2, 6, 2, that still works. If you take a 3, 9, 3, that still works. But anyway, we only needed to identify one eigenvector here. And then basically what I did for lambda 2 equals 1, lambda 3 equals -1, pretty much the same thing. And I guess if I talk a lot about 1, 2, 3, 3, 2, 1, that may confuse you more. So I'm going to pause my video and do let me know if you have any questions. And I'm still running those daily drop-in sessions. So if you have any questions, you can send me email or simply join those drop-in sessions, and we will start from there. Hey, thank you for watching.